Okay. So before we start today's class, we have only left with the last topic, which is nothing but the evaporators. So what I'm requesting today is we will have slightly extended class today, and we will try to complete this evaporator part today itself. So then we are left with two classes, one regular class on Thursday and the tutorial on Wednesday. So we are left with 3-4 tutorials that we can complete in these two classes. Is it okay to everyone? Hello?
Yes, sure.
Other than that, so we are also left with one quiz 2. So can we have a quiz 2 on either Saturday or Sunday, next Saturday or Sunday, same time, same location, which we had earlier? Is it okay? Depending on the availability of the room. Does it make sense to everyone? Is it okay to everyone if we have it on Saturday or Sunday?
Sir, Saturday we have a annual quiz from 10 to
So
12.
Sunday is okay.
Yes.
So I will try to arrange on Sunday. Let me send the request for booking the room today. So tentatively you can consider that the second quiz will be on Sunday. Another thing is I have gone through some of your copies. So before I discuss on that, how was the quiz? Was it good, bad, worst? Any of you? Any comment? How was the quiz? Did you find it easy, difficult? No comment? So both the questions were more or less, based on whatever we have done in the tutorial. But unfortunately, many students have copied as it is the tutorial solution. They have not looked at the statement carefully. In the tutorial, we have solved the problem for a cylindrical geometry. In the question, this sphere was given, and they have copied the solution blindly without even thinking. That was not expected from many of you. Please read the questions carefully, and don't expect me to give the same solution, same question, which we have done in the tutorial, isn't it? It will be slightly different. That is the common sense. That is the common sense, correct? So let me show the solution briefly, and then we will start today's class. Okay, is it fine to everyone?
Yes, yes, sir.
Okay, so this was the first question. As I said that the tutorial which we have done, in the tutorial, instead of a sphere, see here there is a sphere is given. Instead of that, the cylinder was given, and that's why L was coming in here somewhere, isn't it? But in case of sphere, there is no L, there is no length, isn't it? So many people have missed that point, and they have just copied the solution of cylinder as it is without thinking. Okay, so please try to go through all the tutorials carefully. I thought that since these are based on the tutorials, you will find it easy. All right. Okay, so what was the first part? First part was we wanted to find out the heat transfer coefficient, isn't it? So for that, we have compared the rate of heat transfer which we have obtained using the conduction. So for the conduction, the rate of heat transfer can be directly written like this. This is the same conduction equation which we have derived for the spherical geometry, isn't it? So that can be given as 4 pi r into r delta k tv minus tw divided by r delta minus r, and this we can equate to uh, the heat transfer that can be obtained using convection, isn't it? So for convection, you can write the equation as HA delta T, isn't it? So A will be for the sphere 4 pi r square, H into delta T will be TV minus TW. And if you compare these two, what you get is H is obtained as R delta K divided by R into R delta minus R. Many people have obtained the term like ln R delta by R. ln R delta by R you will get in a cylindrical geometry. You don't get that in a spherical geometry. That's a clear indication that you have copied from the solution as it is. And almost 90% students have done the same mistake. Okay, that is the first part. That was straightforward. Second part was we wanted to find out what will be the time t, expression for time t to build the film of thickness R delta. So rate of condensation you can obtain as d by dt, density of the liquid multiplied by the volume. So volume will be given by what? 4 by 3 pi R delta cube minus R delta cube minus R cube. Many people have used here R delta square, R square, and L is multiplied here. So that is the equation for cylindrical geometry, not for the spherical geometry, isn't it? So if you differentiate this entire thing, what you get is 4 pi rho L R delta square dr delta by dt. And this is the rate of condensation. But you wanted to find out how much energy will be used for this, isn't it? So you need to multiply this by latent heat of vaporization, LV. Some students have missed this LV, multiplication of LV here. So if you multiply LV to this, that will be the rate of, heat transfer. And this rate of heat transfer should be given as rate of heat transfer by conduction. So if you compare these two and rearrange all the terms, you get this integral R delta minus R delta square dr delta by R delta. And if you do the integration, you get T is given as R delta cube by 3 minus R into R delta square by 2 plus R cube by 6 and multiplied by LV rho L divided by R K TV minus TW. Okay, just one step answer, 2 steps answer, isn't it? It was not difficult, and it was a similar question was done in the tutorial. So I was expecting many of you to do it correctly. But unfortunately, only few students could do it correctly. So that's not a good sign that students are not going through the tutorials. Okay. Okay, second question. Second question was again, very easy, because what is been given is in the second question, we had a thick walled tube was there, isn't it? And the thick wall of the tube that itself has the electrical current passing through, and that was leading to the dissipation and the generation of the heat. So the amount of heat generated will be given by psi v into pi by 4, basically the volume of this tube, isn't it? So that will be given by what? D naught square minus di square L into pi by 4, and this volume multiplied by psi v will give you the amount of heat generated. So this amount of heat generated should be equal to what? mCp dt, isn't it? So if you compare that, you can directly obtain the L value. That comes out to be 2.27 meter. Some students have only used pi by 4 d naught square or di square. They have not taken the difference. Remember, the heat is generated only in the thick wall of the pipe, isn't it? So that means you need to find out the volume of that particular thing, and not just the internal diameter or the outer diameter. Okay, so from this L you can obtain directly. Now what was the question? Question was asking calculate the compute the heat transfer coefficient at the outlet of the inner surface. Inner surface is clearly mentioned. When it is mentioned clearly, the inner surface mentioned means what? You don't need to calculate the overall heat transfer coefficient. You need to calculate the local heat transfer coefficient, isn't it? So this local heat transfer coefficient will be given by what? H naught will be given by Qs divided by Ts minus T naught, isn't it? The wall heat flux Qs will be given by H naught Ts minus T naught, where T naught is the temperature at the outlet and Ts is the surface temperature, isn't it? So Qs, this Qs multiplied by area will give you the total heat transfer, and that total heat transfer you can equate to the actual total heat transfer, isn't it? Correct. So you can use the H naught Ts minus T naught into this area as same as the amount of heat transfer, and you can calculate H naught. H naught comes around 9750. Many people have used the LMTD here. In the question, it is clearly mentioned that the heat transfer coefficient at the outlet of the inner surface. So that is not the U, capital U. It is just the H at the outlet is been asked in the question. Okay. So again, this was a straightforward, even though I have shown two steps here, but it could have been done in a single step. This total amount of heat transfer here should be given as H naught Ts minus T naught into pi DIL. That's it. Why DIL? Because inner surface is mentioned. That's why inner surface area has to be multiplied, isn't it? And you can calculate this H naught directly. This naught is given for the outlet. Okay, you could have calculated directly H naught as this. Is it clear to everyone? So both the questions were extremely simple. I have specifically designed them as simple so that many of you, since you are coming for the first time for a offline quiz, you should, get some, help. You should not feel that the questions are difficult, because that's it, you are writing the offline quiz after a long period of time, isn't it? So that is why purposefully I have designed the quiz in a simple way. But I think many students are not going through the video lectures and tutorials. So my request to all of you is please go through the videos. Everything is recorded, isn't it? If you have not attended the lectures, doesn't matter. If you have not attended the tutorials, doesn't matter. Please go through the video lectures and video tutorial, because that will aid you significantly. Is it clear to everyone? Hello.
हेलो
हाँ सौरभ बोलिए.
सर, इस क्वेश्चन में मुझे कंफ्यूजन है. इसमें अब ऊपर वाला जो पार्ट है ना, इसी जो मेरे को स्क्रीन दिख रही है अभी, इसमें ऊपर वाला पार्ट है, उसमें जो डायमेंशनली तो जो है वो इक्वल हो नहीं रहे हैं.
क्या है?
देखो जरा, इसमें ना डायमेंशनली चेक करते हैं. जैसे कि पाई लिखा हुआ है, ठीक है. इसकी जो है ऐसा यूनिट है वॉट पर क्यूबिक मीटर, ठीक है. वॉल्यूमेट्रिक है ना ये, रेट ऑफ जनरेशन. तो इसमें ना क्यूबिक तो कट जाएगा, साथ में वॉल्यूम मल्टीप्लाइड है तो क्यूब हट जाएगा, ठीक है. लेफ्ट हैंड साइड मेरे पास वाट रह जाएगा. लेकिन जो राइट हैंड साइड में जो है जो स्पेसिफिक हीट है उसकी ऐसा यूनिट है पर किलोग्राम पर केल्विन. तो इसमें जूल आ जाएगा राइट हैंड साइड में, और लेफ्ट हैंड साइड में हमारे पास वाट. तो मतलब कहने का मतलब कि इसमें टाइमिंग का भी तो आना चाहिए ना.
सो व्हाट इज व्हाट? जूल पर सेकंड.
हाँ.
सो इफ यू पुट दैट इट इज मैचिंग. व्हाट इज व्हाट? What is the equivalence of what? What is joule per second? So it's matching.
लेकिन सर टाइमिंग का कहाँ आ रहा है? टाइमिंग का
मास जो है, मास फ्लो
रेट is given in time ना, kg per minute. So that will become kg per second.
ओके ठीक है. मास फ्लो रेट को हम m नॉट लिखते थे ना, तो इसमें m और m नॉट को ऐसे कंफ्यूजन हो गई.
So there is no dimensional problem in this. Is it correct, everyone? Right? Hello? Does it make sense to everyone, guys?
Yes, sir.
Okay, so please go through. That is the sincere request from my side to all of you. Please go through the video. And I know that after 1 year or 2 year, you are first time coming in the campus and writing the offline examination. It is slightly difficult though. But I can assure you that the quizzes and the exams will be easy. But it will not be very easy that if you go without preparation, you will be able to do it. It will be easy. It will be easy, provided that you go through the material. It will not be difficult. It will not be very difficult questions. It will be very reasonably easy questions. But I request all of you to go through the material. Is it a fair thing to say? Is it? Does it make sense to everyone?
Yes, sir.
Yes, sir.
Okay. All right, guys. So let us start with the today's class on evaporator. So let me share the file. So is my slides visible to everyone? Hello?
Yes, sir.
Okay. So remember how we have started our journey in this particular course. We started with the concept of 3 modes of heat transfer. Then we started with conduction, then convection. In convection, we have looked at the concept of heat transfer coefficient, then forced convection, then natural convection. After that, we started looking at condensation and boiling, and then we looked at the radiation, isn't it? And after that, we have looked at heat transfer equipments. The last bit which is remaining in this entire course is the evaporation. Why evaporation? Because you all are the process engineers. So if you would have been a mechanical engineer, you wouldn't have done this evaporation and boiling and condensation there. Okay, but for a process engineer, this evaporation is extremely important, because if you are working in a process industry, this is what you are going to do. Okay, so evaporation is commonly used in the food processing industry. So you see several products like tomato ketchup or chocolate production or beverage, different liquid beverages, isn't it? Production of salt, sugar, etc. Even milk products. In all these process applications, you will see the evaporation, which is extremely important. Okay, so you being a process engineer, you being a chemical or a biochemical engineer, you will be mostly looking at this type of operations in your in the industry. So that is why evaporation is extremely important. Okay, so why evaporation is used? Evaporation is used for concentrating the liquid beverages to obtain the energy saving in subsequent unit operation. This is very important. Okay. So you wanted to reduce the mass, and for doing that, you wanted to get rid of the solvent from the solution. Okay. Another reason for which the evaporation is used for reducing the weight and volume to obtain the energy saving in storage and transportation. If you reduce the water, basically water is primarily responsible for different biochemical reactions taking place in the food processing, isn't it? So by reducing the water, you reduces the water interaction, and thereby you improve the preservation of the products. Also, sometimes a specific amount of solvent should be present for a desired flavor and color in the products like chocolates. So in all such cases, evaporation is extremely important. Okay, a typical example for their applications is a production of milk, juices, salt, sugar, hard candies, tomato paste and purees, etc. Okay, in fact, if you look at the market of these products, it's a huge market. All these liquid and the food beverages, there is a huge market. Hindustan Liver and TCS, etc. They are working in these areas, isn't it? There is a huge market on this. Is it clear? At least the rationale behind why we are looking at evaporation is clear to everyone. Does it make sense to everyone? Hello?
Yes, sir.
Now, there is a small difference between evaporation and boiling. Don't get confused with that. Evaporation and boiling is same. They are not same. There is a small difference. So the most important difference is evaporation occurs at any temperature. Any temperature. It can occur at any temperature above the melting point. But boiling can occur only at boiling point. Isn't it? So if you are having a water in your pot or something, evaporation can take place between 0 to 100 degrees Celsius, any temperature, isn't it? But boiling can take place only at 100 degrees Celsius. That's what I'm trying to say here. Again, evaporation takes place from the surface of the liquid, whereas boiling phenomena which we have seen, remember there the bubbles formation takes place and eventually the entire fluid is taking part into the boiling. So boiling takes place throughout the liquid. Okay. So generally the heat is supplied from the top surface in case of evaporation. So what happens is the liquid layer which is present at the top, basically that takes part into the evaporation process. So energy is transferred from this top layer, the liquid at the top layer, to evaporate the molecules in the atmosphere. So generally heat is supplied at the top surface, whereas in boiling the heat is typically supplied at the bottom. You heat at the bottom, then the bubbles start forming. These bubbles vigorously move from the liquid pool and eventually escape from the surface, isn't it? That's what we have seen in the boiling. Okay. So as I said, in the evaporation process, only the molecules having the high kinetic energy at the top surface participate. In case of boiling, all molecules in the liquid pool participate. Evaporation process is slow. Boiling can occur rapidly. Okay. Again, the process does not involve the formation of the bubble. Evaporation process does not involve the formation of bubble, whereas the boiling involves the formation of the bubble. So these are the typical, differences between evaporation and boiling. Okay. Another concept is you already know. So what is vapor pressure? So typically if you look at, if there is a liquid there, so you will see that the molecules which are present at the top surface of the liquid, these are bounded only by the layer of the molecules at the bottom. There is no bound, these molecules are not bounded at the top, isn't it? So only these are bounded at the bottom. But if you look at the other liquid molecules, those are present inside the liquid. These are bounded by a top layer as well as a bottom layer, both. These are bounded by top layer as well as bottom layer, both. So you can see that the molecules which are at the top layer, at the surface of the liquid, remember all the molecules are moving zigzag manner because of their kinetic energy. At some time their kinetic energy overcomes this energy barrier required, and because of that these molecules escape from the liquid surface. That's what happens in the evaporation. And since these molecules keep on escaping from the top surface, eventually they build a pressure in the vapor space, and this vapor pressure in the vapor space act on the liquid surface itself, and this pressure is called as a vapor pressure. So the back pressure exerted by the vapor on the liquid surface is called as a vapor pressure. Typically, the vapor pressure varies non-linearly with the temperature. So as you increase the temperature, your vapor pressure is going to increase, but the relationship is non-linear. Again, if you are having a volatile liquid, it will exert more pressure, and therefore vapor pressure of the volatile liquid is higher compared to the non-volatile liquid. Now, what is boiling point? So boiling point is when the vapor pressure of the liquid becomes equals to the atmospheric pressure, the temperature at which the vapor pressure of the liquid becomes the atmospheric pressure, then that particular temperature is called as a boiling point, isn't it? So typically the boiling point of the water is 100 degrees Celsius, but depending on the location it can vary. So if you go to the Mount Everest, your boiling point is lower, that is around 71 degrees Celsius, because the pressure exerted by the atmosphere is very low, and because of that the water can boil at lower temperature. So depending on how much is the dissolved solute or the hydrostatic head present, the boiling point can increase or decrease. Is it clear to everyone?
Yes, sir.
Can we move ahead? Is it clear to everyone? Hello?
Yes, sir.
Okay, all right. So this boiling point elevation, as I said, the presence of solute in the solution can increase the boiling point. And this boiling point elevation is extremely important when we are talking about the evaporation. Why? Because in the evaporation process, what happens? We start with the solution which is dilute. the solution, the concentration of the solute in the solution is very low. But eventually you concentrate this solution so that the amount of the solution becomes small, isn't it? Correct. So to reduce the amount of solution, you evaporate the solvent from the solution, and because of that, eventually the solution get concentrated. As the solution get concentrated, its boiling point also starts increasing. Do you agree with me? Because the more is the mole fraction of the solute. Remember, that is what I said. More is the dissolved solute present in the solution, its boiling point increases, which is called as boiling point elevation. Is it clear to everyone? Hello?
Yes, sir.
Yes, sir.
So how we can calculate the boiling point elevation? This boiling point elevation we can represent using this equation. So here ln xw, xw is the mole fraction of the water in the solution, isn't it? So higher is the solute, lower will be this xw, isn't it? And depending on how lower this xw is, you can find out the new boiling point. So this Tb is the boiling point of the pure water, whereas Tb new is the boiling point of the new boiling point for the concentrated solution. Okay, so 1 by Tb new minus 1 by Tb into L by R, that gives ln xw. So if we know what is the mole fraction of the water in the solution, we can put it in this equation and we can calculate Tb new, because this Tb for a pure water we already know, isn't it? We know this, but we can calculate this using this equation if we know the mole fraction of the water present in the solution. There's another equation which gives a boiling point elevation delta Tb. So this delta Tb is nothing but how much is my boiling point above the boiling point of the pure solvent. If I am using a pure solvent, whatever the boiling point I am going to get, how much my boiling point is elevated beyond this particular point if I am having the solutions, if I am having the solute present in the solution. So that difference is called as a boiling point elevation and represented as delta Tb, and that is given as Kb into m. Here Kb is the constant, molar boiling point constant, whereas this m is the molality. Molality is nothing but number of moles of solute per kg of solution. Is it clear to everyone?
So the
Does it
above
make
equation
sense?
is in terms of mole fraction and the below one is in terms of molality.
Molality, correct. So if we know the molality and the mole fraction, we can put it in this equation. We can calculate how much will be the elevation in the boiling point. Again, I am repeating why the boiling point is elevating. Why the boiling point is elevating?
Because of the
more
presence of solute.
Solute is present in the solution. Correct. Yes. Yes. Okay. So during the evaporation, the solute content increases and therefore the boiling point elevation occurs. So typically you start with the dilute solution, but eventually because of evaporation process, what happens is your solution becomes more and more concentrated, and because of that your boiling points keep on increasing. Okay. Why we are looking at boiling point elevation, that will be very clear to you. Because see, ultimately what we are interested in evaporation, what we are interested in? We are interested in removing the solvent from the solution so that we can concentrate the liquid. That's what we are aiming here. But as the concentration of the solution is increasing, your boiling point is increasing. And because of boiling point increase, what happens is eventually, see, ultimately what you are using for evaporation, you are using a steam. You use a steam, a condensing steam you use for supplying the heat to the solution. And because of that, the evaporation takes place. So that means the temperature difference between steam and the solution, boiling point of this solution, is nothing but the driving force. But as your boiling point is increasing, your driving force starts decreasing. Is it clear to everyone? Yes or no? Does it make sense to everyone? So what is the driving force? Driving force for evaporation is So you are supplying a steam to heat the solution. So that means the temperature of the steam minus boiling point of the solution. This is what nothing but the driving force, isn't it? But this TB is increasing gradually. So what happens to this difference? This difference start decreasing as the concentration increases. Do you agree with me?
Yes, sir.
So that means what? The driving force for the evaporation starts decreasing as the concentration of the solute increases. So this boiling point elevation is extremely important to look at. This TB nu minus TB is extremely important to look at. Does it make sense to everyone what I'm saying?
Sir, what is TB?
TB is the boiling point. So okay, so don't get confused. This is for a pure. Maybe I just put another substitute, TBS. Okay, so TBS is whatever the value of boiling point you will get at a particular concentration. So that will be TB nu in a way. Okay, is it clear? Hello?
Yes, sir.
Is my slides visible or I lost you?
Visible, sir.
Visible, okay, all right. So in the evaporator, if you look at the evaporator, what are the different parts present in the evaporation process? So in the evaporation process, there is a preheater. So this preheater is used for heating the feed because that increases the efficiency. Then there are heat exchanger because steam is used to transfer the heat from steam to the solution. You require a heat exchanger. So there is a heat exchanger used, isn't it? Vacuum pump is used because typically what happens is if you are using a multiple effect evaporator, then the vapor coming out from one evaporator is used as a steam in the another, and very often the driving force you wanted to increase. What is the driving force? TS minus TB, isn't it? So if you lower the boiling point of the solution, higher is the driving force. And how you can lower the boiling point? By creating the vacuum. So vacuum pump is used to lower the boiling point. Is it clear, this third? Hello? Is it clear to everyone?
Vacuum वाला दोबारा समझा दो.
Yes, so if you increase the vacuum, what will happen? Boiling point of the solution, it decreases, isn't it? So that means driving force is TS minus TB, that increases. Correct? Because TB is now decreased.
How does it decrease with vacuum?
So if you use the vacuum, what will be the okay? What is the boiling point of water at Mount Everest?
It's 71 degrees Celsius.
Why it is 71? Why not 100?
Because
pressure at the Mount Everest is low, isn't it?
Yes.
So if you lower the pressure and create the vacuum, what will happen to the boiling point?
It will decrease further.
It will decrease further. So that decrease in the boiling point will lead to increase in the difference between TS minus TB. Correct?
Yes, sir.
So your driving force increases by creating a vacuum. Again, separators are required because whatever the vapor coming out from the evaporator, that you need to condense, and this condensed liquid has to be separated from the non-condensing gas. So separator is used. Okay, is it clear to everyone? At least whatever required equipment is there, is it clear to everyone? We will see the pictorial representation of evaporator that will, clear the concepts further. But is it clear whatever we are saying so far?
Yes, sir.
Okay. So these are the different types of evaporators. Okay, these are the different types of evaporators. So let's look at the first evaporator, the batch type of evaporator. So what we do in the batch type of evaporator, there is a liquid pool is there, and this liquid we are trying to concentrate. Okay, so more the temperature of this liquid is higher will be the vapor formation, and therefore the faster will be the concentration process. Do you agree? If I increase the temperature of this liquid which is present here in the pool, higher will be the vapor formation, isn't it? Evaporation increases with the increase in the temperature of the liquid. Do you agree with me? Hello?
Yes, sir.
So to increase the temperature of the liquid which is present here, what we are doing, there are different tubes are there. So these are nothing but the coils. These are nothing but the coils, and through these coils the steam is flowing, and this steam is getting condensed inside this coil and transferring heat to the liquid here. So because of condensing of the steam, the temperature of the liquid which is inside here in this entire reactor, this temperature of this liquid keeps on increasing, and because of that the vapor formation takes place, and this vapor comes out from the top. Okay, so this type of evaporator is called as a batch type. Is it clear to everyone? Is it clear to everyone?
Sir, for heating, we will be using steam and taking out the condensate in every type of evaporator.
Yes, you are using a steam to heat the liquid, and so that the solvent or the vapor come out from the solution, and eventually it's concentrates. Correct? Does it make sense? Hello?
Yes, sir. Yes, sir.
Your question is whether every time we are using steam or some other liquid can be used. That is what the question is.
No, sir. The question is we can do it by bringing it direct contact with the energy source, heat source. Why we
Direct contact
are
with the energy source, like
direct putting it on some kind of fire or the reactor.
so you are saying I just
By
create a
by heat
fire at the
transfer is
bottom
we
here
just
and evaporate, is it? But then it's not, then it's not a evaporation, then it could be a boiling. Make sense?
oh, so okay, so that is the reason.
Okay, and also that is not desirable. So see, one thing is that, but that is also not desirable sometimes, because what type of product we are looking at here? Tell me. These are the food products. Okay, these are the food products. This could be tomato puree, or this could be chocolate syrup. If you are heating them with a very high temperature at the bottom, what will happen?
They will burn or something like that.
Some degradation will take place. Yes. So that is why instead of heating here, we use the evaporators. Even in the evaporators also, we are cautious not to degrade the product, because most of the time evaporators are used for food products. So degradation of the product is extremely important. Extremely important. And degradation basically takes place when we are exposing the product to a high temperature, or we are exposing the product for a moderate temperature but for a higher time. Residence time is higher or the temperature is higher. In that case, the degradation takes place. So both we try to minimize whenever the sensitive products are there. Is it clear?
Yes, sir.
Does it make sense? So you all will see this experiment. So triple effect evaporator experiment is there in your CLP 303 or 305. I don't remember exactly the name, but in your lab you will see the evaporator, triple effect evaporator. Okay, is it clear to everyone?
Yes, sir.
Okay, so this is a batch type. Why we are saying it batch type? Because here the liquid we have added as a batch, and then we are concentrating directly in the this evaporator itself. We are not moving this liquid in a so unlike a flow contacting pattern, here we are not moving the liquid at all. Okay, so that's why we are calling this as a batch type. There is another type of the evaporator which is a natural circulation type. So what is happening here is, so feed we have taken as the input from this inlet here. Okay, and this feed is moving up directly here because of natural circulation. Why natural circulation? So what is happening here? The steam is flowing through this jacket outside here. The steam is flowing through this jacket, and this steam flowing through this jacket steam flowing through this jacket here is basically hitting the liquid, and because of hitting of this liquid, what will happen? The density of this liquid is going to decrease, and that this liquid is going to move like this, isn't it? So there is a natural circulation is generated because of density difference created by heating of the steam. Is it clear to everyone? Is it clear?
Yes, sir.
So this automatically this liquid circulates like this because of density difference. That's why we are calling this as a natural circulation. So feed is input from this direction, goes up, comes down here, the vapor is separated here, and the concentrated liquid is taken out here as a product. Is it clear to everyone? The natural circulation?
Yes, sir.
In a forced circulation, instead of having this natural circulation because of density difference, now we are using a pump to flow the liquid, isn't it? So this is same as natural circulation, except that the liquid is now being circulated inside this evaporator by using a pump. That is the only difference. That's why it is called as a forced circulation. Is it clear to everyone? Hello, is it clear?
Yes, sir.
So unlike these two, what is the difference with respect to these two in a rising film? In a rising film, because of density difference, the feed is going up. So unlike this, there is a recirculation is taking place. Here the recirculation is taking place, but here there is no recirculation. In this rising film, there is no recirculation here. Can you see? The feed is directly coming in and the product is coming out here. There is no recirculation. This is not coming here. That is the difference between these 2, 3 and 4. Is it clear to everyone? Correct?
Yes, sir.
So here film is rising because of density difference. So the liquid is getting heated because of condensing steam which is flowing through the jacket, and because of that the fluid is moving up using the density difference. That's why it is called as a rising film. Even you can pump it, so that even in that case also it will be called as a rising film. But unlike this, when the fluid is move up and fall down like this, in this case you can see that the liquid is falling down, forming a film here, isn't it? And eventually this drops here and the vapor is separated here. This type of arrangement is called as a falling film evaporator. Is it clear? So here the liquid is moving in this direction, falling here. Unlike this, in this case, the liquid is moving in this direction from bottom to top. In this case, the liquid is falling from top to bottom. Clear? Here. Is it clear?
Yes, sir.
So this is called as a falling film evaporator. And the last one is the agitated thin film. Now this is a very interesting design. Remember, the heat transfer is taking place where? Heat transfer taking place in this jacket here. Yes or no? So what is the resistance to the heat transfer? The resistance to heat transfer is a film thickness. That's what we have seen in the condensation. Do you agree with me? Higher is the thickness of the film on this particular metal part, lower will be the heat transfer. Do you agree? Do you agree with me or not?
Yes, sir.
But if I scrap the film which is present here at the surface, then I can increase the heat transfer. Do you agree? Yes or no?
Yes, sir.
And that's what is occurring here in the agitated film. This agitator is scrapping the thickness of the film forming here. And because of that, it leads to a higher heat transfer rate. Is it clear to everyone? Can you see the point why the agitator is used? Because that agitator moves like this and it scraps the film which is present at the periphery. And because of scrapping of the film, the thickness of the film is very small here, and that eventually leads to a higher heat transfer coefficient. Make sense to everyone?
Yes, sir.
Okay. All right. Is my slide We lost the slide.
Yes, sir.
Just a minute. Let me share the file. Is it visible?
Yes.
The slides are visible?
Yes, sir.
Okay, all right. So this agitated thin film is done. Okay, now let's define some of the terms in the evaporator. So first important term is the capacity. So capacity of the evaporator is defined as the amount of water vaporized per unit time. Amount of water vaporized per unit time in the evaporator is called as a capacity of the evaporator. There is another interesting term which is called as a steam economy. Remember, as I said, that in the evaporation process you supply the heat using the steam, isn't it? And because of that the vapor is getting formed over the liquid or a solution, isn't it? So amount of steam, amount of water vapor produced, typically the solution involves the water. So amount of water vapor produced per kg of the steam used is called as a steam economy. Is it clear? This is a very interesting term. Both these terms are very important term. Capacity is the amount of water vaporized per hour, per unit time. That is the capacity. But amount of water vaporized per kg of the steam used is nothing but the steam capacity, steam economy, sorry. Amount of the kg of water vaporized per kg of steam used is called as a steam economy. And usually the steam economy of the single effect evaporator is less than 1 or it is approaching to 1. Is it clear? Hello?
Yes, sir.
Both these terms are clear?
Yes, sir.
So now very often we desire to have the higher steam economy. That means we want to have more amount of water to be vaporized per kg of the steam used. That means we wanted to improve the steam economy beyond 1. How that can be done? That can be done by using 3 ways. One is using the preheaters. So whatever the water vapor coming out from the evaporator, those water vapor we can use again to preheat the feed. Preheat the feed, because that will kind of lead to a energy saving, because the temperature of the feed is increased, and this increased temperature of the feed, this higher temperature feed is then further heated by the steam. So eventually there is a energy saving takes place, and because of that the steam economy increases. That means the amount of water vapor produced per kg of steam used can be improved by using the preheaters. Another way is to use the parabolic trough collector. What is parabolic trough collector? Parabolic trough collector is a mechanical device or is a solar device which concentrates the solar power. So whatever the solar rays are coming, those solar rays are concentrated using this parabolic trough collector. And these concentrated solar radiations are then used to heat or preheat the feed. So you improve the steam economy by using the preheaters or parabolic trough collectors. Is it clear to everyone, this first point? Hello?
Sir, tell once again about the parabolic trough collector.
So parabolic trough collector is what? It's a, so see, solar panel you have seen.
Yes, sir.
So it is similar to the solar panel, but instead of generating the electricity, what it does is it concentrates these solar rays, and these concentrated solar rays then produces the heat, and this heat is then used for heating the feed.
Yes, sir, got it.
Clear?
Yes, sir.
So something like this, maybe I'll just try to draw. So
Yeah.
you are having a mirror, something like this. So whatever the solar radiations are reaching to this, all these are concentrated at one location. Okay, and the liquid is flowing through this. So this liquid is heated because of the solar radiations concentrated here. Can you see the point?
Yes, sir.
So this is one way of improving the steam economy. But most commonly used ways for increasing the steam economy is by using the multiple effect evaporator. So here you can see that we have used only one evaporator. But let's say if I use such evaporators in series, let's say I use this natural circulation evaporator in a series. So one unit is this. Again, the product coming out from this is used as a feed to the next evaporator here, and the product coming from that is used as a feed to the third one. So multiple such concatenating of individual units can be used in a multiple effect evaporators. Is it clear to everyone what I'm trying to say? Is it clear?
Yes, sir.
So by using multiple effect evaporators, we can improve the steam economy significantly. It can go beyond one. It can easily go beyond one. The another methodology for improving the steam economy is a vapor recompression, and this is very important. Vapor recompression does what? So whatever the vapor coming out from the one effect, that vapor is compressed using the compressor. So once you compress the vapor, what happens to it? When you compress the vapor, its boiling point increases and its enthalpy increases. And this compressed vapor then act as a steam to the next effect. So vapor recompression is a very important methodology for improving the steam economy. Why? Because this is what the method used in the nuclear reactors. So if some of you join a DAE, Department of Atomic Energy, this is what you are going to use there. The rationale behind using the vapor recompression is vapor recompression does not increase the volume of the fluid used. That is a very important statement. Why? Because in the nuclear reactor, whatever the solvents you are using, these solvents usually have the radioactive material. So if you increase the volume of this radioactive material, you will require additional money to discard it. You will not be able to throw the radioactive material anywhere, isn't it? That has to be concentrated and that has to be dumped into a specific location. You will not be able to dump the nuclear waste anywhere, isn't it? So there the rationale is to minimize the amount of fluid used. And vapor recompression method is the method which can give a very effective evaporation without increasing the quantity of solvent used, quantity of the steam used. Is it clear to everyone? Hello? Can you see the point? We will see some more details on this as we go ahead, but at least the rationale or at least what is the philosophy behind all these three methods is clear to everyone? Hello?
Yes.
So in multiple effect evaporator, I said we will use multiple such unit one after another where the product from one is act as a feed. Okay. Act as a feed here, and this is the product. So and the vapor coming out from here is used as a steam here. Vapor coming out from here used as a steam here. That's what is used in the multiple effect evaporator. So let's look at each of these in little bit more detail so that you will appreciate what I'm trying to say. Is my slides visible or I lost you?
Visible.
Okay. So one of the commonly used method for improving the steam economy. What is steam economy? The kg of vapor produced per kg of steam used that can go beyond one by using multiple effect evaporator or by using a vapor recompression. So let's look at multiple effect evaporator first and then we will look at vapor recompression. Okay, both these methods are extremely popular in the industry. In fact, one of the lab experiment is on multiple effect evaporator. So 3 effect evaporator you will be looking at in your CLP 303 or 305 in the next semester. Okay, so that you will practically see in the lab. Okay, so in multiple effect evaporator, what we do, we use the multiple single effect evaporator one after another in a series. Okay, to improve the steam economy. So it involves the use of vapor generated in one effect as a heating medium in the next effect. That is what I said, isn't it? So vapor generated in first effect is used as a steam for the next effect, and this vapor generated in the next effect is used as a steam to the further downstream. Okay. So the significantly reduces the amount of steam, because now the steam you are using only in the first effect. You are not using the steam in the second or the third effect, isn't it? In the second and the third effect, the vapor generated from the previous effect you are using as a steam, isn't it? So no additional steam is used in second and the third effect, and because of that, the amount of steam consumed decreases significantly compared to the amount of water evaporated. Clear? Is it clear to everyone? Hello?
Yes, sir.
But if you are using the vapor from the previous effect as a steam to the next effect, clearly the boiling point in the next effect has to be lowered. Then and there only a vapor which is generated from the previous effect will act as a steam, isn't it? So in each subsequent effect, the boiling point of the feed need to be reduced by lowering the pressure. So there this vacuum comes into the picture. So thus the required delta T is created by generating the vacuum. Okay. All right. In triple effect evaporator, the capacity of each effect is generally the capacity. Capacity is what? The amount of steam, amount of vapor generated per hour, isn't it? Per unit time, that is called the capacity. So capacity is generally 1/3 of the single effect evaporator in case of triple effect evaporator with the same terminal temperatures. Again, usually, okay. So then you can argue that why don't we use the large number of effects one after another? There is a trade-off involved, because each effect you are adding, each additional unit you are adding incurs a cost. Of course, you are having a saving in terms of the steam used, but then you are also requiring, you also require the cost in terms of creating the vacuum, and also you requires the cost in terms of the new unit which is added. So usually a trade-off exists between the increase in number of effects and the saving in terms of steam economy. The optimum number of evaporators is determined by analyzing the cost required for setting up the additional effect and the saving in the steam economy. Is it clear? This third point is clear? Correct? Yes or no? So what I'm trying to say here is, if I add multiple effects one after another, like this, I can have steam economy increase. This steam economy is going to increase, but additional unit added like this will have fixed cost. Also, in each subsequent unit, so here whatever the TB is there, boiling point is there, TB1, this TB1, TB2, this is let's say TB3, and this is let's say TB4. So you can see that since the vapor generated here act as a steam here, and vapor generated here act as a steam here, vapor generated here act as a steam here. Okay, so in order to have this vapor generated here act as a steam in the next effect, this TB2 has to be lower than TB1, and you can lower this TB1 by using vacuum, and this vacuum, for creating a vacuum you require a cost. So there is a trade-off between how much cost required for setting up the additional unit and whatever is the saving in terms of steam economy. Is it clear to everyone?
Yes, sir.
Okay, Further, in a multiple effect evaporator, so see here I have shown that this vapor act as a steam here in the next effect, but the product, okay, so feed I have added here, so feed I have added here, feed, this is the feed, okay, and the product coming from here is act as a feed in the next effect, product coming here act as a feed in the next effect, product here, feed here, and the product coming out. So clearly you can see that this type of arrangement where the feed and the vapor both are moving in the same direction, this is called as a forward feed arrangement. But you can have a reverse feed also. So there are different possibilities where the feed is moving in the same direction or same direction of the vapor, then it is called as a forward feed. There could be a backward feed, there could be a parallel feed. So different arrangements of the feed are there depending on what type of product you are looking at. Okay, so let's look at these arrangements in the next slides. Okay, so you will appreciate what I'm trying to say. Is my slides visible? Hello? Hello?
Yes, sir. Visible.
Okay, all right. So this is a single effect evaporator. So in the single effect evaporator, this liquid is heated by the condensing steam. The vapor is coming out from here. This vapor is condensed here in the condenser, and the liquid is taken here as another product, and the non-condensing vapors are discarded to the atmosphere. Okay, this is the single effect evaporator. Here steam economy is in generally less than 1. But let's look at the multiple effect evaporator. So this is the triple effect evaporator. So here you can see that we are adding a feed in the first effect. This feed is heated using a steam. So typically the pressure, if you are using 1 atmospheric pressure, the boiling point here is 99 or 100 degrees Celsius, nearly 100 degrees Celsius, isn't it? But the vapor coming out from this first effect is then act as a steam to the next effect, isn't it? So in order to have this vapor acting as a steam to the next effect, the temperature, the boiling temperature here in the next effect should be lowered. And in order to lower the boiling temperature here, what we have to do? We have to reduce the pressure. And therefore the pressure used in the second effect evaporator is 40 kilopascal, which is less than this. So at this pressure, the boiling point is 74.6. So the product coming out from the first effect then act as a feed here in the second effect. And again, the vapor generated in the second effect is used as a steam to the next third effect. Condensate is coming out here. The product coming out from the second effect is used as a feed to the third effect. And finally, the product coming out from the third effect is used as the final product. And the vapor generated here is condensed here. Okay, so this is a triple effect evaporator. So here you can see that the feed and the vapor both are moving in the same direction. This is called as a forward feed triple effect evaporator. Okay, so pressure is subsequently reduced in each of these effects in order to facilitate the evaporation. Correct. Again, the steam is used, originally the steam is used in the first effect itself. Subsequent effect use the vapor. Correct. So the amount of steam used is much lower compared to if you are using a single effect evaporator like this. So the steam economy is usually greater than 1. Is it clear to everyone? Hello? Is it clear to everyone?
Yes, sir.
Now, as I said that there are multiple combinations of the feed are there. So this is the forward feed. Here you can see that the feed is entering in the first effect, the product coming out from the first effect then used as a feed to the next effect. Then the product coming from the second effect is used as a feed to the third effect. So in this case, we do not require a pump because all the subsequent effects are having the lower pressure. So here, whatever the pressure I am having, compared to that, the pressure in the effect 2 is lower. Again, the pressure in effect 3 is lower than 2 and 1, isn't it? So clearly the feed or the product coming up from the first effect is sucked in the second effect directly. So we do not require a pump in this case. This is a forward feed. But let's say if I use the feed in a reverse direction. So for instance, if I use the feed in the third effect, whereas the vapor is moving in this direction. Okay, so you can see that the vapor generated from the first effect is used as a steam in the second, and vapor generated in the second is used as a steam in the third, and in the first effect for heating only the pure steam is used. So in this case, you can see that the feed is coming directly in the third effect, and the product coming from the third effect then used as a feed to the second effect. So clearly here the product coming out from the third effect has to move to the second effect, which is at a higher pressure. Remember, here the pressure in the third will be lower, pressure in the two will be higher. So we have to transfer the product from the third effect to the second effect, which is at the higher pressure. So clearly you require a pump here. Is it clear to everyone? Does it make sense?
Sir, is there any
Sir, how we
advantage
are
of using the backward feed over the forward feed?
Can you see here? Remember, in each of the subsequent effect, the boiling point temperature has to be lowered. This lower boiling point you can get only by reducing the pressure. So vacuum has to be created here. Unless or until you create a vacuum, the boiling point will not be reduced. And unless you reduce the boiling point, the vapor coming out from the previous effect will not act as a steam. Can you see the point? The vapor coming out from this particular effect can act as a steam to the third effect only if the boiling point of the liquid in the third effect is significantly lower. Then and then only that delta T will be created. See, if I transfer the liquid present here directly here without lowering the pressure, what will happen? There is no delta T, because whatever the temperature here is TB and this temperature is also TB, so there is no delta T. That delta T you are creating by creating a vacuum here or vacuum here. Does it make sense? So you can see that in each subsequent steps, in each subsequent effects, the pressure decreases, and decreases in the sense, we should not say decrease, we need to decrease by creating a vacuum. So we decrease the pressure in subsequent effect in order to facilitate the vapor to act as a steam in subsequent effect. Is it clear to everyone what we are saying? Hello? Does it make sense? Hello? Please say something. If something is not clear, say no. I will again explain. Hello? Am I audible?
Yes, sir.
Is it
Yes,
clear
sir,
or
you
not
are,
clear?
and it's clear.
Okay,
It's
all right.
clear.
So we have to lower the pressure as we move from effect 1 to effect 2, effect 2 to effect 3. Clear? And since the pressure is getting lowered, in a forward feed doesn't matter, because the lower pressure is here. So this feed product from the first effect will be sucked into the second effect. The product from the second will be sucked into the third automatically without any pump. But if you are having a backward feed, remember here the feed is moving in this direction as the direction of the vapor. But in this case, the feed is moving in the reverse direction. So feed is entering into a third stage instead of entering into the first stage in the forward feed. Here the feed is entering in the first stage or a first effect. Unlike that, the feed is entering into a third stage in the triple effect evaporator. Can you see? Hello? Can you see the point?
Yes, sir.
So clearly the product coming here will be at a lower pressure, but the pressure inside this 2 is higher. So if I have to transfer the feed from lower pressure to higher pressure, what I have to do? I have to pump it, isn't it? I have to pump it. In this case, it will be automatically sucked in, but in this case, you have to pump. Can you see the point? Hello?
Sir, if we are using pump, the energy requirement will
Yes, of course. Energy
somehow
requirement will be
increase. Then,
higher. Yes, absolutely. Energy requirement will
then
be
what is the
higher.
point of
But
Then what
the
is the point of
point here
using-
is why. Okay, so you are saying that why one should use the backward feed compared to forward feed. That's what the
Yes,
question
sir.
is.
Yes, sir.
Okay, so in the backward feed, what happens is the feed is exposed to a very high gradient directly here in the third stage. So what will happen is most of the evaporation is going to take place in the third stage itself. So you require, so in subsequent effect, you will be treating the lower amount of feed compared to what you are treating in the third stage, isn't it? So that is the advantage. Can you see the point?
Yes.
So even though you are incurring more energy here, but at the same time you are removing more vapor direct in the first stage itself without transferring it to the other two stages. See the point?
Yes, sir.
Okay, so that is the advantage. Okay, so in comparison with forward feed and backward feed, there is a parallel feed. So parallel feed is what? So in the parallel feed, what we are doing is this feed we are entering into the first stage itself. But unlike that, we are entering this feed to all three stages simultaneously. Here you can see that this feed is segregated into three streams: stream 1, stream 2, and stream 3. So we are feeding effect 1, effect 2, effect 3 simultaneously. And the product coming from 1, 2, 3 are directly taken out instead of transferring it to the effect 2 and effect 3. Why we are doing this? Because in this case, the residence time of the feed in this heated medium is decreased, and parallel feed is therefore very often is used when the residence time required is lower. This is used whenever we are having the product which is heat sensitive. So in case of heat sensitive food, we are using the parallel feed. Very often we use the combination of forward feed and backward feed, which is called as a mixed feed arrangement. Okay, is it clear to everyone? Different combinations. Hello. So combination of mixed feed and backward feed is called as a mixed feed. When we are, supplying the feed to all three effects simultaneously, then it is called as a parallel feed. And the product coming out from all three effects are taken out together. It is not transferred to the next effect. That is what we are doing it in a parallel feed. Can you see the point here? Hello? Is it clear to everyone?
Yes, sir.
Okay, all right. The another concept is a vapor recompression. So vapor recompression, it involves the compression of the vapor generated from the evaporator. So by compressing the, if you compress the vapor, what we are doing? By compressing the vapor, we are increasing its enthalpy because you are increasing its boiling point. So boiling point of the vapor increased. So see, in all these effects, what we are doing? We are lowering the boiling point of the liquid here, isn't it? You are lowering the boiling point of the liquid here. But at the same time, I can increase the boiling point of the steam here or enthalpy of the steam here instead of lowering this. Instead of creating the vacuum, if I compress this vapor coming out here, compress here, I will have a higher enthalpy vapor present, isn't it? And that higher enthalpy vapor will be higher enthalpy and a higher boiling point vapor will act as a steam directly instead of lowering the temperature here. Can you see the point? That's what is used in the vapor recompression. Instead of creating a vacuum for the liquid, we are compressing the vapor, which is acting as a steam to the next effect. By compressing the vapor, we are increasing its enthalpy, we are increasing its boiling point, and by doing that, we are creating this delta T. By doing that, we are creating the driving force. Can you see the point? Hello? Hello? The concept is clear or not clear?
Yes, sir. Clear.
So instead of creating a vacuum and reducing the boiling point of the liquid, we are increasing the enthalpy or the boiling point of the vapor itself, which is acting as a steam. So instead of reducing the pressure here, we can use the same feed here, but the compressed vapor here act as a steam. So we do not require lowering the temperature or lowering the pressure here in the subsequent stages. So this particular methodology is called as a vapor recompression. So such recompression of the vapor is performed thermally or mechanically. Okay, so there are two recompression methods, thermally and mechanically. So in thermal recompression, so let's say in a plant, if you are having a very high pressure steam available for some other operation, so but for a particular operation you require a lower pressure steam. So this high pressure steam is used in a steam jet ejector to lower its pressure, but then it is compressing the vapor directly, and that compressed vapor is then used as a steam to the next effect. Okay, so compression of the vapor is performed using steam jet ejector. In this case, the compression of the vapor is performed using mechanical compressor. So there is a difference. Here the high pressure steam is already present for some other operation, and that high pressure steam is used using a steam jet ejector to compress the vapor. This is used whenever the steam with high pressure is available and much lower pressure is required for the operation. This is used when the limited amount of steam is available for the operation. Again, the thermal recompression can handle the large volume of the vapor and is preferred for vacuum operation, whereas the mechanical recompression is used when the dilute radioactive solutions, concentration of dilute radioactive solution and production of the distilled water. So as I said, mechanical recompression is used because you require very less amount of steam used. So you are not contaminating the solvent further. So amount of waste generated in the nuclear plant has to be minimized because that has to be disposed of later on. And mechanical recompression helps in reducing that amount of waste generated. And because of that, mechanical recompression is commonly used in a nuclear plant instead of using a thermal recompression or a multiple effect evaporators. Okay, so mechanical efficiency is low in case of thermal recompression, but mechanical efficiency is high in case of the mechanical recompression. Again, this has a flexibility, so you can increase the effect by using, you know, more compressor. More rated compressor if you use, higher will be the recompression. So flexibility is there. But in case of thermal recompression, that flexibility is not there. So typically, if you use the mechanical recompression, you can generate the effect which is equivalent to as good as 15 effects. The only problem in case of mechanical recompression is you require a lot of, you know, energy or power for compression. That is the only drawback. But this can lead to the effect similar to equivalent to the 15 effect evaporator. So multiple effect evaporator, if you use 15 effects, that equivalence you can generate using the mechanical recompression. Is it clear? These points will be clear once you see their operation schematically. Is it clear what I'm saying here so far? Hello? Is it clear or not clear? Hello?
Yes, sir, clear.
Okay, so these two things will be clear in the next slide. Okay, so what is happening in a thermal recompression? So in a thermal recompression, what I'm saying is steam with a higher pressure is available. So if you are having a higher pressure steam available with you, you don't use directly here for heating. Instead of that, the vapor generated from this evaporator, you are mixing with the steam in a steam jet ejector, and because of that you get a lower pressure steam, and that lower pressure steam you are using as a condensing medium. So thermal recompression uses the steam jet ejector. So high pressure steam is converted to the lower pressure steam using a throttling process, which is shown here in the steam jet ejector. So whatever the vapor you are generated here, that get compressed slightly using the high pressure steam. So this is something called as a thermal recompression. Okay, so you do not have a much flexibility here in this particular operation. But if the vapor generated from the evaporator, if you are compressing it using the external compressor, and only a small amount of makeup steam you are adding in this entire operation, whatever the compressed vapor is, that itself is used as a steam. Only a small amount of makeup steam is used in addition to this for heating the liquid. So in this case, you can see that you have a lot of flexibility, because if you wanted to improve the effect further, you can increase the compression here. So if you increase the compression, this arrangement will give you a higher, this arrangement will give you a effect equivalent to a higher effect evaporators. Is it clear to everyone? Yes or no? So you do not require a multiple equipments, multiple effects added one after another in both these arrangements, but the effect will be equivalent to multiple effect evaporator. The effect will be, sorry, the overall performance will be equivalent to the multiple effect, but you require only one single unit. You do not require a multiple unit which are used here. So that is the advantage. Can you see the point in a vapor recompression? So in a multiple effect evaporator, multiple units are added. In a vapor recompression, you are not adding a multiple effects, but you are creating that effect by compressing the vapor coming out from the evaporator itself. So this vapor itself is used as a steam here, but you are compressing that, and by compressing, you are creating the equivalent impact of that of the multiple effect evaporator. Is it clear? Hello? Does it make sense?
Yes, sir.
All right. So is it possible for you guys to, stay for 15-20 minutes? Only 3-4 slides are there. Then we are done with our syllabus. Do you want to do it now or in the next class? In the next class, anyway, we need to do the tutorials. Is it okay if I exceed for 15-20 minutes?
Yes, sir.
I'm really sorry to extending, but it should not be in the cost of your understanding. So are you all able to understand what I'm saying? Hello? Okay, all right. Okay. Okay, so let's continue with the design. So last topic remaining is the design of the evaporator. This is very important. This is very important because most of the questions which you are going to see on this topic will be on the design. So far we have looked at the concept. In the vapor recompression, what we said is, instead of adding the multiple units as that in the multiple effect evaporator, you can have the same impact in the single unit itself by compressing the vapor. That's what we have said in the vapor recompression. Now let's look at the design of multiple effect evaporator. So in the multiple effect evaporator, let's look at the forward feed, how the design is performed. So this is the first effect. Whatever the product generated here is acting as a feed to the next effect. Hello? Hello? Can we take a break of 2-3 minutes and come back? Hello?
Yes, sure.
Let's take the break of 3-4 minutes and we will again 2-3 minutes, maximum 2-3 minutes break, and then we will again continue. Okay, so that you will also gather the energy. Let me also gather the energy so that you can we all can do this very important topic in a much more detail and in a peaceful manner. Okay, so give me 2-3 minutes, maximum 2-3 minutes. Okay, all right.
Sir, we have to leave this meeting or
you keep the meeting as it is, don't leave. Okay, we will join in 2-3 minutes. Okay, all right.
yes, sir.
Okay. हेलो, हाँ जी बोलिए, हाँ बोलिए। Okay. Okay, so can we continue? Hello. Sorry for the interruption because can we continue, guys? Hello, are you all around?
Yes, sir.
Okay, so let me share the file. Okay, is it visible? The slides are visible to everyone? Hello?
Yes, sir.
Okay, all right. So what we were saying here is, so the last topic which we have looked at is a vapor recompression. We said that the same impact as that of multiple effect evaporator can be obtained by using vapor recompression. In a vapor recompression, instead of adding a multiple unit one after another, we do not require that. Instead of that, the vapor is compressed and that compressed vapor itself is used as a steam. So by doing that, instead of adding multiple units one after another, we can have the impact same as multiple effect evaporator only in the single unit itself. That's what we generally achieve in a vapor recompression. Now, let's look at the design of multiple effect evaporator. So this is one of the most important topic in this particular chapter. So in this case, we are looking at a forward feed triple effect evaporator. Here you can see that the feed is entering in the first effect, and the product coming out from the first effect is then used as a feed to the second effect. Again, the product coming out from the second effect is used as a feed to the third effect, and the product coming out from the third effect then finally used as a product. The steam is used in the first effect to heat the solution. So the vapor generated from the first effect then used as a steam to the second effect, and also the vapor generated from the second effect is used as a steam to the third effect. Here in this case, you can see that the pressure P1 and TB1 will be higher than P2 TB2. Again, P2 TB2 will be higher than P2 TB3. This should be TB3. This should be TB3. Okay. So whenever you are solving any problem of the evaporator, the first step, please listen carefully. Whenever you are solving a triple effect or any evaporator problem, first make a schematic diagram like this. First make a schematic diagram like this, because if you make the schematic diagram like this, then your solution procedure becomes very easy. So what I'm trying to say here is, whenever you are solving any problem of the multiple effect evaporator, just make a simple diagram like this.
Sir, are the pressure same in effect 2 and 3?
No, that also I have to change. So thank you. So first make a schematic diagram like this. So steam in, product in, product out. In this manner, you make a schematic diagram. Okay. Once you make a schematic diagram, denote the variables here. So what is the input heat to the first effect? Input heat is by steam, isn't it? So steam is represented by This is the flow rate of the steam. This is the temperature of the steam. This is the enthalpy of the steam, which is denoted by I, and the pressure of the steam is PS. So you show all the variables here. Okay, then with respect to the feed, this is the feed, isn't it? With respect to the feed, what is the flow rate of the feed? What is the enthalpy of the feed? What is the temperature of the feed? That you denote here. Again, the vapor is forming in the first effect. So vapor will be generated. What is the flow rate of the vapor generated? That is given by WS1. Enthalpy of the vapor is IS1. T1 and P1 is the temperature and the pressure of the vapor generated. Here the subscript 1 denotes the effect 1. Okay, this should be P3. This should be P3. Okay, this I will correct. Now, why in a similar manner you can denote WS2, IS2, T2, P2, WS3, IS3, T3, P3, and clearly the feed coming out from here, product coming out from here will be act as a feed to the next effect here. But the amount coming out from the first effect will be what? We have added WF, and out of this WF, WS1 is separated. So the feed to the second effect will be what? WF minus WS1. Do you all agree? Yes or no? Correct?
Yes, sir.
Similarly, from WF minus WS1, the WS2 is separated. So the feed added to the third effect will be what? WF, WS1, WF minus WS1 minus WS2. And I2 is its enthalpy, TB2 is the temperature. Similarly, here the product coming out will be what? WF minus WS1 minus WS2 minus WS3. Correct. Again, note down that this TB1 and this T1 may not be same. Why may not be same? Because this TB1 is what? In this case, the solution is concentrated, and solution is concentrated, and because of that its boiling point will be what? It will be elevated. So TB1 is including the boiling point elevation. So TB1 will be higher compared to T1. T1 is nothing but the boiling point of the pure solvent. Remember, this is the vapor. So vapor is a pure solvent. So T1 is a boiling point of a pure solvent. T2 is a boiling point of a pure solvent at P2, and T3 is a boiling point of a pure solvent at P3, isn't it? And this T1, T2, T3 may not be same as TB1, TB2, TB3. So we can take TB1 and T1 same only if the concentration of the solute present here is very low, isn't it? When the solution is extremely dilute, in that case we ignore the boiling point elevation. Boiling point elevation. We ignore the boiling point elevation if the solution is having a very low concentration. Okay, then and then only we ignore the boiling point elevation. Otherwise, we have to include the boiling point elevation, and in that case, TB1 and T1 will not be same. But when we ignore the boiling point elevation, this TB1 and T1 is same. Okay, so in this entire figure, once you denote all these variables, then you can make the energy balance. So now energy balance to the first effect will be what? So energy coming to the first effect, the energy coming to the first effect by what? So there is a energy coming in by steam. There is a energy coming in by the feed, isn't it? So WF into IF is nothing but what? WF is the flow rate of the feed multiplied by its enthalpy is the energy coming in terms of feed. WSIS is nothing but what? Flow rate of the steam multiplied by its enthalpy. So this is the energy coming into the first effect. Do you all agree? Do you all agree with me?
Yes, sir.
Now what is coming out from the first effect? So coming out is the product coming out from the first effect is WF minus IS1. So WF minus IS1 is the amount of product coming out from the first effect multiplied by enthalpy is the amount of energy coming out from the first effect. Similarly, this vapor is coming out at the top. So WS1 IS1 is going to be the amount of energy coming out in terms of the vapor, correct? and also the steam is getting condensed. So Ws into IL is the amount of energy coming out in terms of the condensate. Do you all agree? Yes or no? Does it make sense? This energy balance makes sense to everyone?
Yes, sir.
So typically whenever you are solving the, is my slides visible?
Yes, sir, visible.
So whenever you are solving any evaporator problem or whenever you are designing the evaporators, first make a schematic. Once you make a schematic, then everything becomes very, clear. Otherwise, if you write this equation directly without making the schematic, you will be lost, because this is clear for a forward feed. But let's say if I use a backward feed, then in the backward feed, remember in the backward feed, WF IF will be here. In a backward feed, if I use a backward feed, instead of this, I will have a input here, and that input here will be what? WF IF. Do you agree with me or not? In a backward feed.
Yes, sir.
Instead of this, I will have here what? I will have WF minus WS3 IS3 I2. Do you agree? And what will be here? WF minus WS3 minus WS2. And here coming out will be what? WF minus WS3 minus WS2 minus WS1. So things changes depending on what contacting pattern. If you are using a forward feed, this is okay, but this red is for backward feed. Backward feed. If you use a parallel feed, you will get a different equation. So depending on what type of contacting you are having, this equation changes. Correct. This I have written only for first effect, but I can write a similar equation for the second effect and the third effect. Do you all agree with me? So therefore make a figure, make a small schematic diagram before writing the energy balance equation. Does it make sense to everyone? Hello?
Yes, sir.
Okay. Is my slides visible?
Yes, sir, visible.
So now let's look at the design concepts here. So now this equation number one, further we can simplify by assuming that if we assume that this steam is a condensing steam, that means it is a saturated steam. If you assume that this steam is a saturated steam, means what? We do not have any sensible heat. We only have a latent heat of vaporization. So this equation gets simplified immensely, because if I'm using a latent heat of vaporization here, this second factor here, WSIS, becomes what? WS lambda S. Correct? Latent heat is lambda S. And we do not require this enthalpy term IS here and IL here, because saturated steam is condensing at the fixed temperature. So this IF and IL I can get rid of. Can you see the point? Hello? If I use a saturated steam, my equation becomes simplified like this. WF IF, WS lambda S, WF minus WS1 I1 plus WS1 IS1. Yes or no?
Yes, sir.
Again, for a second and third effect, we can write down a similar energy balance equations. So for a second effect, what is the input? For a second effect, the input is WF minus WS1, that is the input feed, and WS1 here is acting as a steam. So my equation becomes WF minus WS1 I1, that's the enthalpy of the feed, plus WS1 lambda S1, why lambda S1 here? Because this WS1 is acting as a steam, saturated steam. So lambda S1. Do you agree? Hello? Do you agree with me? Make
Yes,
sense or not? And this is the input. What is the output? Output from the first effect, second effect. The output is this Wf minus Ws1 Ws2 multiplied by I2. That will give me the energy output. What will be the energy output in the terms of vapor? Ws2 Is2. So Ws2 Is2 is the output. Similarly, we can write down the energy balance equation for the third effect. Okay. So input will be Wf minus Ws1 minus Ws2. That is what the input is. See, this is the input. This is also input. So Ws2 lambda S2 will be the input, and output will be Wf minus Ws1 minus Ws2 minus Ws3 into I3 plus Ws3 Is3. That's what we have written. In addition to these three equations, one more equation will be there. And what that equation will be? What that equation will be? You can find out, if you know what is the feed and what is the output, you can find out how much amount vaporized. So you can pinpointedly find out Ws1 plus Ws2 plus Ws3. So you will have four equations. These three equations plus fourth equation will be Ws1 plus Ws2 plus Ws3. That summation you will be knowing. So you will have these three equations and four equations and four unknowns. Remember, in this four equation, what are the unknown? Unknown are Ws1, Ws2, Ws3 and Ws. These are the four unknown and four equations are there. So in addition to these three equations, one more additional equation you will have, and that additional equation will be this Ws1 plus Ws2 plus Ws3, and that will be equal to some quantity. This will be known to you. So these four equations and four unknowns are there. What are the four unknowns? Four unknowns are Ws, Ws1, Ws2 and Ws3. These four unknown you can calculate by using four equations, four simultaneous linear equations. You can calculate four unknowns. Okay. Now these we have calculated from the energy balance, but also we can represent this in terms of the heat transfer. Now heat transfer is occurring in all three effects. So what is the heat transfer occurring here? Whatever the steam you have added, that is giving the total heat to this, isn't it? So Ws into lambda S should be the total amount of heat transfer to the first effect, and the amount of heat transfer given by what? UA delta T. Yes or no? UA delta T is the amount of heat transfer. So amount of heat transfer will be given by this UA delta T, where U is the overall heat transfer coefficient for the first effect, U2 is the overall heat transfer coefficient for the second effect, U3 is the overall heat transfer coefficient for the third effect, and the amount of heat transferred will be given by UA1 Ts minus TB1 for the first effect. For the second effect, we will have U2A2 TW1 minus TB2. And for the third effect, U3A3 TW2 minus TB3, isn't it? Note that this TW1 is not same as TB1. Note that TW2 is not same as TB2. Why? Because the boiling, these are the boiling point temperature of the pure solvent, whereas TB1 and TB2 are, these include boiling point elevation. Boiling point elevation. But if you are using a dilute solution, then these are same. Then these you can use here. Only in case of dilute solution. Okay, so from this equation, these are equation number 5 and 5, 6, 7. These equation gives me the heat transfer occurring in individual units. Okay, individual effects. Now, whenever you are designing the evaporators, remember in the multiple effect evaporators, you are having the same unit repeated multiple times. And if you are designing it, it is advisable to design each of these units of the same size. Because if you are designing these individual effects of different size, you will require more construction and design cost. But if you design of the same size, then the same equipment you can repeat one after another. So your design and manufacturing cost decreases significantly if you design it of the same size. Very often, as a matter of practice, the heat transfer areas in all effects are taken to be equal, and also to keep the size of the same effect same, because this significantly reduces the equipment cost. So if you design all your effects of same size, same area, then your cost of manufacturing decreases. Okay. So with this assumption, there are 3 steps involved in the design of the evaporators. In the first step, an initial estimate of the temperature in each effect is made. In making this estimate, it is assumed that the heat transfer rates in 3 effects are roughly same. So remember, in this case, we have obtained these 3 equations: U1 A1 delta T1, U2 A2 delta T2, U3 A3 delta T3. If we assume that the area is same and the rate of heat transfer is same, in that case what happens is we can equate these 3 equations. So this is the assumption. We are assuming that the rate of heat transfer is same. We are using this assumption in order to get the initial estimate. Once we get the estimate, then we are going to do all these energy balance. We are going to find out WS1, WS2, WS3, and we can calculate the individual areas. And if these areas are same, we stop there. If the individual areas are same, then our assumption is correct. But if these individual areas are not same, then we redistribute the temperature. And again do the calculation. So this procedure is iterative procedure. We start with the initial assumption that the rate of heat transfer is same. Based on that, we calculate delta T1, delta T2, delta T3. Based on that, we again delta T1, delta T2, delta T3. Once we have calculated, we know the individual values of these temperatures here. Based on that, we can calculate the enthalpies here. And once we calculate the enthalpies here, we can use these balance equations. We calculate WS1, WS2, WS3. Once we know WS1, WS2, we can calculate individual areas. Check whether these areas are same or not. If these are not same, then we perform this trial and error again for the next cycle till we get the areas same. So there are 3 steps involved in the design. Hello?
Yes, sir.
Is it becoming too much? Sorry. Is it becoming too much? Maybe, okay. Is it possible to have an extra class today in the afternoon or maybe tomorrow? I think this is a very important concept, but okay, maybe we stop here and we will continue this entire thing again on a Thursday. Only one slide is there. After that, 2 examples are there, but these are very important things, and I am really reluctant to do it in a hurry because I think. Are you all able to get it what I'm saying, or we are lost? Okay, maybe let's stop here. We will continue with these concepts again on the Thursday class, but then we need one more lecture for the tutorials. So can we have one extra class maybe on Wednesday or Tuesday for tutorials? We will do the tutorials. We will not do the regular class on that. Is it possible?
Yes, sir.
When we can have a extra tutorial class?
Sir, when it is scheduled, like we have decided, no, Wednesday.
Wednesday we will have one, but in addition to that, I'm saying.
Sir, you can extend that, I think.
Yes, sir.
Okay, maybe let me just complete this, and we can do in a regular class on a Thursday. We will do a recap of this everything again. Is that okay? Because I think these concepts are very interesting, and I think we are already 2 hours almost.
Sir, one thing, could you repeat the one, the last slide which you explained?
Okay.
I wanted to ask that why we are considering area to be equal and then putting it again in the equation.
Okay.
Until
So area,
we
okay,
get
area rationale behind using the area to be equal is because in general we design the same unit. We do not design a different size unit. We design a same size unit and we use them repeatedly in multiple effects. So the size of effect 1 and size of effect 2 and size of effect 3 all are same, and heat transfer is taking place at this jacket itself. And if the size of all 3 effects are same, what will be its area, heat transfer area?
equal.
Equal.
But
This is the
we
reason why
can
we are
have it
using equal. Okay, now that is what the point is. So here what we are doing is there are 3 steps involved in this. There are 3 steps involved in the design process. What we are assuming is we are initially, in order to get, see, we have to start with some assumption in order to design. So in order to start the calculation, we are assuming initially the rate of heat transfer is same. Rate of heat transfer is same. That's a reasonable assumption because size of all my units are same, isn't it? So I am assuming that the rate of heat transfer is same. Of course, the rate of heat transfer will not be exactly same because the temperatures are different, but that's a valid assumption to start with. So we are assuming the rate of heat transfer are same. So because of that, U1 A1 delta T1, U2 A2 delta T2, U3 A3 delta T3, all 3 are same. And since the areas are going to be same because these are the same size units. So areas are same. So A1, A2, A3 all are same. So based on this, U1 we know, U2 we know, U3 we know. By knowing U1, U2, U3, and we also know the terminal temperatures. So for instance, if I'm looking at this, I know what is the temperature of the steam here, and I know what will be the outlet temperature of the feed here. Okay, so if I know the terminal temperatures, or any 2 temperatures, we can find out delta T1, delta T2 and delta T3. See, if we know the terminal temperatures delta T, we can find out delta T1, delta T2, delta T3 from these 3 equations. Is it clear to everyone? Once we know delta T1, delta T2, delta T3, then based on the individual values of the, once we know delta T1, delta T2, delta T3, we can know the individual values of T1, T2, T3, etc. Remember, delta T1 is nothing but this temperature difference. If you know the temperature difference here, TB1 we know. If you know this temperature difference, if you know this TS, I can find out T1. Similarly, once I found out T1, from T1, I can find out T2. From T2, I can find out T3. Isn't it? So similarly, I can find out all these temperatures. So once I know these temperatures, I can go back and find out what will be the enthalpy from the charts given backside of the book. Okay, once I know the enthalpies, once I know the, in this case, enthalpy, instead of enthalpies, I will have the lambda, isn't it? Latent heat of vaporization. So latent heat of vaporization for saturated steam for a given temperature, I can find out from the tables given backside of the book. Once I know that, I can put those in these equations. And then I can calculate these individual values of WS, WS1 and WS2. Once I know WS, WS1, WS2, I can back calculate the areas. So remember, we started with the hypothesis that A1, A2, A3 should be same, but now we are getting a different values of A1, A2, A3. That means this temperature difference delta T1, delta T2, delta T3, these are are not correct. These are not correct, isn't it? Terminal temperatures are okay, but individual distribution in delta T1, delta T2, delta T3 is not correct. So we can redistribute these individual temperatures. And by redistributing individual temperatures, again we go ahead for the next iteration. And in the next iteration, again we calculate A1, A2, A3. If A1, A2, A3 are not same, then we will again redistribute the temperatures, and we will continue this cycle till our areas are coming out to be nearly the same. That's how the design procedure is used. Again, in this entire calculation, see, delta T1, delta T2, delta T3, this should be equals to Ts minus TW3 minus boiling point elevation. So this calculation of boiling point elevation becomes very important whenever I am having a concentrated solution. But when I am having a dilute solution, this I can neglect. But if I am having a concentrated solution, in that case, this boiling point elevation can also roughly we can calculate. We can assume that the amount of evaporation we can calculate, total evaporation, and 1/3 of that will be taking place in each of these effects. With this, we can calculate the concentration present in each effect. Once we know the concentration of the solute present in each effect, we can use this equation and we can calculate the boiling point elevation. And that boiling point elevation one can use this equation. Okay, so that procedure becomes slightly more tedious when the boiling point elevation cannot be neglected. But very often when we are only concentrating the dilute solution, this summation of boiling point elevation we can neglect. Is it clear to everyone? So you will appreciate all this concept when you look the solution of the problems. Once we look at the solution of these problems, then you will appreciate the concepts. Okay, so we stop here, but in the next class we will take the recap of this design procedure, and then we will try to see the solution of these two solved examples, and then we will look at the tutorial examples. Is it clear to everyone?
Yes.
So we stop here and we will continue from this point onward in the next class. Again, one more announcement I wanted to make. Tomorrow 2 o'clock, please come to my office and you can collect all your quiz copies. Okay, tomorrow 2 o'clock. Is it okay to everyone?
Sir, can you tell where your office is?
That is block
Yes.
1 311. Block 1 311. From my office tomorrow 2 o'clock, collect your quiz 1 copies. And sorry for extending little bit. Thank you so much for the patience. But we will not require any extra class. We will cover everything on the next Thursday class. And also we will do 1 or 2 tutorial on that regular class. And one more tutorial class we are having on Wednesday. So we will not be requiring any extra class beyond that. Our examination quiz 2 will be on Sunday. Can we stop here? Hello? We will do slightly more, detailed recap of whatever we have covered towards the end, so that, everything becomes clear to you again, one more time. Is it clear? Hello?
Yes, sir, clear.
Okay, thank you so much. Let us stop here. And sorry for